So this is the second type of reaction and the second mechanism that you need to know for halogenoalkanes. The last one I put in my previous video on nucleophilic substitution, which is a really nice intuitive mechanism where the curly arrows just make sense. Whereas for this mechanism, slightly less so, but it's fine. You're here. We'll get through it together. Now, before we get into the mechanism, let's make sure we understand just what elimination reactions are. Elimination reactions, or in elimination reactions, we are removing a group. And in the elimination of halogenoalkanes and also alcohols, which we'll see in a future video, we end up producing an alkene. So if we were to write some sort of general equation, which I'll write as kind of a mix between word and symbol so that we can get a real good idea. Yeah, really good idea of what's going on. If we start with our halogenoalkane, and as an ionic equation, if we react that with hydroxide ions, OH-, then we are going to produce an alkene. We're going to produce water, and we're going to produce a halide ion, right? And that halide ion will depend, of course, on what the halo group was in your original halogenoalkane. So your X could be, so that could be Cl-, Br-, I- as your standard ones. I mean, technically F-, but not really. Okay, so first thing that we should think about, of course, OH- is not a reagent. You cannot pick up a bottle of OH-. So where is this going to come from? The OH- comes from typically sodium hydroxide. And you might be thinking, again, especially if you watch my last video, hang on a second, isn't OH- a nucleophile because there's a lone pair and it's going to just attack the partially positive carbon and we're going to get nucleophilic substitution? The answer is yes, right? OH- will do that. But OH- can also be the sodium hydroxide rather can also be the reagent in elimination reactions. Both of those could happen. We could get nucleophilic substitution and or elimination depending on the reaction conditions. So for nucleophilic substitution, let's even just write as a reminder. For nucleophilic substitution, we had our sodium hydroxide and it was aqueous, right? Dissolved in water. Whereas for elimination, our sodium hydroxide is going to be, specifically, it's going to be hot. And instead of being dissolved in water, so in aqueous solution, it's going to be dissolved in ethanol. So we say that it is ethanolic. Now, careful here, that's not ethanoic, like ethanoic acid. It is ethanolic, meaning dissolved in ethanol. Ethanol is the solvent. I want to make sure you've got that. Okay, so hot ethanolic sodium hydroxide, we get elimination. Just aqueous sodium hydroxide, we get nucleophilic substitution, again, like we saw in my last video. So head back there for a reminder of how that mechanism works. And as mentioned before, these will be our products. So let me outline the mechanism. We'll do a couple of examples because this mechanism, and to be fair, whenever we are producing an alkene, we get some nice crossover to our isomerism topics. So to start, this might look really familiar because we've got chloroethane and we've got hydroxide ions. Now, and I keep saying this, when it comes to nucleophilic substitution, yes, our lone pair on our hydroxide ion would attack our partially positive carbon and kick out the chloro, and we'd just be swapping. However, if we have hot ethanolic sodium hydroxide, instead of acting as a nucleophile, our hydroxide ion is going to act as a base. And a base is a proton or an H+ acceptor. So for this mechanism, instead of attacking a carbon atom, the hydroxide is going to take an H+. And which H+ is it going to take? It takes one on a carbon that is adjacent to the carbon that's attached to our halogen. So this is our carbon attached to our halogen, which means that the adjacent one is this carbon over here, the one next to it. So for our first curly arrow, we'll have a curly arrow from the middle of the lone pair on the hydroxide to the H on the adjacent C. And then this leads to a kind of like domino effect. So this mechanism can be quite satisfying to draw because the arrows just kind of follow one after another. So once the hydroxide has taken this H, that causes this CH bond to break, which puts those electrons forming a double bond between these two carbons. And because that carbon would now have too many bonds, that means that this CCl bond is going to have to break. And that's it. So what do we end up with? We would now have, if we think about our two carbons here, we'd now have a carbon-carbon double bond. The carbon on the left has lost this hydrogen, so it just has these two hydrogens left. And then the carbon on the right has lost this Cl, so it's just got these two hydrogens left. And so we have produced from chloroethane, we now have ethene and alkene. We've also produced from this H combined with this OH, HOH, aka H2O. And from this Cl that's fallen off with these electrons, we've also got Cl minus. I'm going to put the lone pair here again, just so you can see how those electrons are traveling. Now, of course, because we wouldn't have just been using OH minus, like I said before, you can't just pick up OH minus in a bottle. This would have come from sodium hydroxide, which means that our Cl minus would be attached to that sodium ion. So in the same way, let's just put it here, this hydroxide came from sodium hydroxide, which means that this Cl minus will actually give us NaCl. Okay, but we don't need to include the sodium ion here because it's spectating. It is not involved in the mechanism, so we don't need to include it. It's just kind of taking up space and is more likely to lead to some sort of mistake being made. So this is your this is your most simple example for your mechanism. We accept an H plus using the hydroxide. That forms a CC double bond and then kicks out the halo as a halide. Now, as I mentioned before, this has a really nice crossover with isomerism, both structural isomerism and stereoisomerism. And I'm going to use one super common compound to show you both examples now. So let's start by looking at where structural isomerism in our product might come about. Well, remember, structural isomerism, that's where they have the same molecular formulae, but different structural formulae. And the reason we can get structural isomers is because, as mentioned before, the hydroxide ion acting as a base is going to accept an H+. And where is that H+ coming from? It's coming from a hydrogen that is on a carbon adjacent to the CX carbon, right? Now, in our first example, there was only one possible carbon that was adjacent to give that hydrogen up. Whereas for this second example, we have got two adjacent carbon atoms with hydrogen atoms attached, which means the hydroxide has two options, right? It could take this H or it could take this H. And because this molecule is not symmetrical, that's going to lead to two different products. So let's follow both of them with curly arrows. If we took, let's start with the red one. So attacking and stealing that H, and then we would get our carbon-carbon double bond forming here between carbons 1 and 2. And then, of course, kicking out the chloro group, we would end, oh, I don't want that pen. We would get, what would we get? So carbon-carbon double bond forming between carbons 1 and 2. Carbon on the end has got two hydrogens. That's really wonky, but you'll hopefully forgive me. Second carbon only has one, and then 2, and then 3. Okay, that's option number 1. That is but-1-ene. Whereas if instead we took that green hydrogen, let's just start here as well, then we're now forming that carbon-carbon double bond between carbons 2 and 3 instead, right? Same mechanism, just a different H+ being accepted. And then we'll end up with our carbon-carbon double bond between carbons 2 and 3. And hopefully you can already name this with me, which is but2-ene. Right? So these are structural isomers. More specifically, they are position isomers because our functional group, which is our carbon-carbon double bond, is in a different position. Okay? But, and however, when it comes to producing alkenes, right? If your product is an alkene, oh my goodness, as well as like structural isomerism, you should also always, and I repeat, you should always look out for EZ isomerism, right? That doesn't mean it's always going to be there, but that should be your final check. If you've got an alkene, is there EZ isomerism? And as a quick reminder, but there'll be a whole video on this where we go through this in more detail, to have EZ isomerism, we need restricted rotation, so which in this case is around a carbon-carbon double bond. And we need 2 different groups on each of those carbons in that carbon-carbon double bond. Okay, so if we now look at our 2 structural isomers, do either of these also have the characteristics, right? The credentials, I don't know, to have EZ isomerism as well. Well, if we look at but1-ene, of course, you've got the carbon-carbon double bond. We've got that in both. But for but1-ene, on this carbon on the left, we don't have 2 different groups on that carbon, right? We've got both of these are the same. They're both H's. So we are not going to have EZ isomerism. However, if we go over here to but2-ene, on each of these carbons in the carbon-carbon double bond, we've got 2 different groups. We've got an H on each of them, and we've got, a CH3, which means that those H's and CH3s can be positioned either on opposite sides, making it the E. Oh, I don't like that. On opposite sides, making it the E, or on the same side, making it the Z isomer. So do we have space to draw those both out? I think we should. I think it's important. So if we start with maybe our E isomer, where around our carbon-carbon double bond, we have our groups, our priority groups on opposite sides. So we can have our H up and our CH3 down. And then we can have our CH3 up and our H down. This would be E. Or we could have our groups on the same side. So both H's up and both CH3s down as our Z. So, summary, reminder, elimination mechanism, ethanolic hydroxide acting as a base. We can get structural isomerism, but if we have 2 adjacent carbons with hydrogens, and we should also always look out for EZ isomerism in our alkenes by considering whether there are 2 different groups on each of the carbons involved in that carbon-carbon double bond. Okay, for more practice, make sure that you check out my my TikToks, right? I've got more examples of more mechanisms with more, did I say more examples? More examples, lots more examples. Make sure that for more A-level chemistry explanations and practice, you have subscribed to my channel, you've liked this video, and comment with any questions. And I will see you in, let me move out the way, in the next one.